Okay, so now in this video, we are going to take a look at our first question in this particular worksheet, and it asks you to draw a nucleophilic addition mechanism. So please note that you are only required to draw for step 1. Okay, so it's just this one. Actually, we know from our theory that the full reagents and conditions for step 1 should be HCN with trace KCN and heats. But of course, we don't need to write that. Okay, actually, just out of interest to link this back to theory, the reason why we need to have trace KCN here is because HCN on its own is quite a weak acid, so it doesn't dissociate fully to give us the CN minus nucleophile that we want. That's why we need to have a KCN catalyst, um, which actually provides some of the CN minus as well. Okay, so now glycolic acid is this one, but we don't need to think about step 2. We just need to think about what is our starting uh, reagent. So our starting reagent here is methanol, HCHO, and it is an aldehyde. Now, if you ever forget, how do I know that this is an addition reaction? Because my methanol, HCHO, is an unsaturated compound. So what's another unsaturated compound that you know in your syllabus? Or rather, what's a functional group that is found in unsaturated compounds? Your alkenes. And alkenes also undergo addition. So just remember, addition is across a double bond. Whether it's across a CO double bond or a CC double bond, it's an addition reaction. And we know that it's nucleophilic addition because um, it is, we have a delta plus carbon over here. This carbon over here is delta plus, it's electron deficient because it is bonded to a highly electronegative atom O. That's how we know that we need a nucleophile to attack this delta plus carbon, and therefore this is a nucleophilic addition mechanism. Of course, if you have your head clear, very clear in the exam, and you can think, oh, HCHO, this is a carbonyl compound, then I mentally flip back to my topic on carbonyl compounds. Oh, this must be nucleophilic addition. Yes, you can do that. But in prelims and in A level, a lot of your questions are going to be synoptic. So you may not always be entirely clear on what topic you are being tested on. So please just read the question, respond to the question. Okay, this is very important, especially in paper 3, when you have a lot of long synoptic questions. Okay, now let's get into the mechanism proper. First step in writing any mechanism in H2 chemistry, name the mechanism. This will at least get you 1 mark. Okay, if I'm not wrong, this particular past year A-level question, this thing was 4 marks. So naming the mechanism, even if you don't know anything else, will at least score you 1 mark. But let's try to get more than 1 mark, shall we? Let us start. We know that this is a 2-step mechanism, so let's draw our reactants first. HCHO, methanol. Now, remember, in general, sometimes the question, actually quite often the question will give you this particular line here or some variation of this particular line. So even if you don't remember the checklist for this specific mechanism, or even you've lost your head completely and don't remember the checklist for organic mechanisms in general, usually some variation of this line will be provided in the question. Please use this as a guide. Okay, so what happens in this particular mechanism is, first, I need to include lone pairs, dipoles, and curly arrows. In my reactant, do I have any lone pairs? Yes, I have 2 lone pairs on my O, and therefore do I have a dipole? Yes, because now my O is delta minus because of the presence of these lone pairs. My C is delta plus. So delta plus and delta minus, what's going to happen is that one of the electron pairs in the CO double bond is going to attack the oxygen atom. And at the same time, I'm going to have a, let's change color, I have a CN nucleophile here. So this CN, I must indicate the negative charge, I must indicate the lone pair. Now, my carbon is an electrophilic site, it's delta plus. So this lone pair, I start my curly arrow from the middle of the lone pair. I come here and I attack my delta plus carbon. And of course, this is a slow step. And then therefore, this is going to form a tetrahedral intermediate. So because my O has now gained one extra lone pair of electrons, we need to indicate a negative charge on the O. And then my H and my H stay the same, but then now I have a Cn that is bonded. So I form a tetrahedral intermediate that is an alkoxide ion. This O with the negative charge is an alkoxide ion, in case you haven't realized. And then, second step, we can just copy this over, more or less. Second step, you need to know that this lone pair on the O is going to protonate an undissociated molecule of HCN. And of course, HCN, I also need to indicate that here I have a delta plus, I have a delta minus. Please, please, please be very precise here. My curly arrow should point to the C on Cn. Don't go, do not draw like that. Don't point in between. That is conceptually incorrect. Also, please don't draw like that and point to the end. This is also conceptually incorrect. Your curly arrow needs to go from the HC bond to the C. Okay? You don't need to show the C and triple bond. And this is a fast step. So what is going to happen now is I'm going to have H bonded to the C. Now this H is now OH. Now that the O has protonated the H, so these two green electrons here will form my OH bond. My Cn, my purple Cn is unchanged. But then because this HC bond has undergone heterolytic fission, I have a new Cn minus nucleophile. So in a sense, just like in electrophilic substitution, I have a homogeneous catalyst that is regenerated at the end of the reaction. And that is it for this particular example of nucleophilic addition. But just make it a good habit to double check that whatever product you have drawn here fits the molecular formula here. And yeah, we're done. If you want to, you can also think about, actually I think I'll just do it now lah. Just to revise a bit of synthesis as well. Over here I have Cn. How do I convert my, do I have any other colors? No. Okay, never mind. I'll just use blue lah. How do I, no, green. Okay, sorry. Okay, how do I convert my Cn to a CO2H? Obviously, number one, my step one has been a step-up reaction such that I add one extra carbon. But then now I need to convert a Cn to a CO2H. So we actually learned this all the way back in halogen derivatives. I originally had this particular compound, and then I want to convert this particular compound. So whatever is on the left side remains the same, but instead of Cn, I have COOH. So this is, Cn is a nitrile. So I'm having acid hydrolysis of a nitrile. So this is dilutes H2SO4 and heats under flux. Okay, this is not part of the question. I'm just revising a bit of synthesis here, just so that you remember something. And can I get this nicely? Yes, I can. Okay, yeah, that's pretty much it for question 1 with a little extension. Of course, hope you guys enjoyed it. Thank you. And we are going to go on to the next mechanism now on nucleophilic substitution.